I think it's live. I think it's live. I think it is actually live. Yeah, I like this new zoom level on my machine. I've actually found myself I'm finding myself actually using. I'm trying to sit half in the sun, half because it gets warmer. Sorry if you can't see me clearly, but let me know. So what are we gonna do today? What we want to actually do is to add immediate instructions to our RISC CPU instruction set. Yes. We want to actually handle immediate instructions. And immediate instructions is sort of this, so there's 6 of them. There's store, branch, register, immediate, upper immediate, jump. These are the types of instructions. These are kind of 6. And they all handle like stuff. Like jump handles loops. Branches handles, basically if else it handles branches. And then store, I think that works with actually either loading or storing to memory. I'm not so clear on that. I haven't got it there yet. What I want to add today is basically immediate mode, not immediate mode, just immediate type instructions to our CPU. Because currently we have this CPU, tiny, not that one. That's a different CPU. But currently we have this tiny CPU, and it only handles the register to register instructions. So we do like an increment, an add, a sub, an and, an or, an XOR, and a shift left and a shift right. These are all quite cool, but if you notice something, they don't really work out the way they should, because in register to register, before we even get to func 7, we do have func 3, and func 3, these 2 fields extend the opcode to specify the operation to be performed. So there's still we need to fix up how we're handling func 3, and then we need to add, I think, 3 instructions that go with immediate. So that is, I think, add I, and then there's something like there's can I remember them? It's add I, sub I, and what is it? Add I, and I, or I. These are the 3. It's actually just 3. That's why I chose immediate, because those are the simple ones. But infusing immediate into our code will immediately change it. I didn't mean to say immediately. Infusing immediate into our code will start changing it so that it starts working towards the RISC-V standard. And if actually the thing that this will force us to do, because immediates have 12 bits, as you can see here. Immediates have 12 bits, as you can see here. So this will actually force us to move from this ROM of 8 bits, 8-bit ROM, to a 32-bit ROM, which means we're starting to become RISC-V. We're still RISC style, but with this one, I think with this change, we're now actually in the process of actually becoming RISC-V. So that's what I'm gonna do today, and try and figure out how to basically end up adding immediate mode. It's really simple. It's just adding enough logic and registers so that we can handle these instructions properly. We need to start using register destination, RD, which is the destination register. We do need to start using RS1 and RS2, which is kind of the things that we need to be the things that we are handed. So this will start making it become a very actual production CPU, which is quite cool for me, I think. So let's actually change some code, shall we? I do not have any code editor open, so let's do that. And then I'll go into where are we? go cd something documents, I think, and then in documents I will go to HDL, and then in here I'll go cd tiny CPU here, and then here I want to know which branch I am on. So git branch. I actually want to be on main because the test bench is waiting for some reviews, and then I will come back to that. Check out main, and then let's actually git checkout dash b pr move add immediate type. So I'm starting to now check out branches and use PRs, because if I can't do this all in one sitting, then this needs to sit somewhere so that we can come back to it later. And I want to push up the code, so in case you're following along and you want the code and you want to make some changes, you can do that. Yeah, so that's kind of what I want to do. I'm not gonna do too much explaining today. What I think I'll do is just jump straight into the code and start working, and then I'll try and stop every few minutes and go check the YouTube link for questions. Hey Tomas, how are you? Should I call you Tomas or should I call you Bartholomew? You should let me know. I hope you're cool, man. Let's do some code. Thank you for coming today. Okay, cool. So we're in here, and yeah, like I said, I'm gonna be jumping into the YouTube thing in every few minutes to answer questions. So let's do the first change. The first thing we need to do in order to accommodate this, in order to accommodate this. Wait, so which window is this? Why does it look like that? Okay, cool. So in order to accommodate this 11 bits, we basically need to move from an 8-bit register to a 32-bit register for the ROM memory, so that our instructions can be 32-bit. Because now we need to do something that contains 12 bits in it. As you can see, 20 to 31, so 12 bits. So let's do that. The first thing we need to do here is move to 07, so we need to go to 31. That makes our instruction code 32 bits. Yeah, that does that. And then let's actually define here. Let's define yeah, sorry. I like having the afternoon sun because it's warm, and I live in a cold part of the Western Cape right now. And it's spring, but it's still cold. And I have all these allergies and stuff and whatever. So let's actually make some conveniences access registers. So I want to make this kind of map, especially this one for register and immediate. This kind of map where we can like have something like immediate or func7 or rs2 or rs1, and we can just refer to or opcode or all of this. So we can just refer to them as a name, and that way it's easier to actually access stuff. Yeah, actually, yeah. Let's do that. So let's do that. Let's make some wires. Convenience wires. I don't know if you remember about wires, but if you do remember about wires, they have some default value, and it's somewhere. That's not good. I have a cough. So wires. So there's something called wires. Wire. Let's see, what is a wire? So a wire is a net of some sort. Actually, let's put it here. A wire is a net of some sort, and what it does is it holds. Cool. Yeah, nets correspond to physical wires that connect instances. The default range of a wire or a reg is 1 bit. So you can make groups of bits. You can make groups of bits for that you can, because the default range is 1 wire, but you can make a group of any. And the group there is going to really help us, because then we are able to access these, you see, like you can call func7, rs2, rs1, func3, rd, opcode. You can just use those names to actually access them. So let's actually make, let's make something of the sort in the first place. So I think I'll do a reg 31.0. And then I'll call this the IR register. That's the instruction register. And then in here, I will now actually start breaking them apart. You see? So I can do something like wire 60. I think so. I can do that. And then I can name this opcode. And then I can say this is IR, something like, how do we choose indexes? Do we say the big one to this one? Yeah, IR 620, same thing. Boom. So now we have an opcode. That's basically what we have. So 620 here, opcode. You see, we have an opcode. We can actually later in our code we can just call opcode. We can just use opcode. You see, and that will actually fix stuff for us. And then we can do a wire. RD is 7 to 11, that is 5. 1, 2, 3, 4, 5. That is at 5. So we can do 40 wire 40, and then we can call this RD, and then we can do this. We can call this equals to IR, and then this starts from 11 to 7. That's 5, isn't it? 11 to 7. 11 to 7. Yeah, that seems right to me. And then we can say wire, and then we can call it, we can make a func3, so that is 3 bits, 12 to 14. This is going to be 30, isn't it? That's the capacity, and then we can call it func3, and then we can say equals, and then here we can say IR, that's going to be 12, 14, 12. Yeah, so that's just a subset of it. And then we can say wire here, and then the next part we want to do is let's do RS1 and RS2, and those are both 15 to 19 and 20 to 24, and that is like both of them are 5 bits, so 40, and then RS1. Actually, I just like it like that. IR, it's this is RS1 is 15 to 19, so 15, 19. Is that okay? Does that make sense? And then I'll do wire. This is 40 as well, and then this is going to be RS2, and then this is the second operand or the first operand. So you get when an instruction is using 1 or 2 operands, you use this basically. I think 24, 20, something like that. And then no. So this is going to be this has been done wrong. This is 19 to 15. Yes. And then we still need to finish all the way to 32-bit, and then we need to make 60. This is which one is this? This is going to be func7. Do we need to do func7 right now? We're not going to even use it, but I will put it in because it just makes later when we get to handling I think jumps and system calls, we can actually call these ones. Okay, 31 to 25. Yeah, so all I did was I made this sort of map, this one, 31 to 25 func7, there it is. And then RS2 is 20 to 24. Let's see. RS2 is 20 to 24. Okay. RS1 is 19 to 15. RS1 is 19 to 15. Okay. And then func3 is next. Is 14 to 12. That's 14 to 12. That's fine. And then we made an RD. And then that is RD is here, which is 11 to 7. And then that is actually 11 to 7. That's fine. And then we made an opcode, which is 6 to 0, which is now 6 to 0. That makes sense. And then we need to do. I actually had to ask for at work for this, and we need to make. Immediate mode holds signed bits. This holds signed bits for. It basically allows us to determine whether an operand is signed or not signed. And immediate mode is for actually working on constants. We get to see this later a bit on down the road, but whenever your compiler runs through your code and makes it into some sort of assembler, what happens is it optimizes a lot of things into constants. And most constants that the code that it optimizes to are between negative 2047 and positive 2048. And basically this the 12 bits allows us to do that. If you went just no signed, you'd go to 4096 again. This is again sort of binning again. Something that you know from somewhere else suddenly appears in another field. Okay. So really what we want to do is we want to be able to build signs for this. And this immediate 12 bits it holds like sign bits for us to, the 31st bit or the 32nd bit holds a sign. And if 1 is for like negatives and 0 is for like positives or something, we don't have to deal with that right now, but basically it holds a sign, and whenever we have that sign, we can use that to, if one of your operands was something like -5, you would use this register to identify that something is negative or positive. And because of the optimization of the compiler, you'll end up with a lot of constants in your assembly, and this makes it faster, because quite a lot instead of going to fetch a constant and operate on it, you can actually embed the constant in the instruction itself, and then you can use it. That's really what immediate helps us with. So we need to do some sort of jumping around with registers so that we can end up with the signed and the immediate. So we can do like wire, we can call it signed, if I remember correctly, and then we can give this, it's 31 all the way to 20. So that's do we make it the whole thing? Oh yeah, let's do that. Rather than, because we're not using IR again, we're using, let's make that, and then we do immediate I. And then in here we're gonna like chunk down the thing. So we're gonna take the first 20. We're gonna replicate the first 20 the first register. Whatever is in 31. Where's my mouse? Okay. Whatever is in 31, we're gonna copy it over all the way to 20. That's what we want to do, so that we can maintain the sign of the bit. So here we're going to do that, and then we copy that into IR 20, and then we say IR, and then in here we say 31. 20 times what is in IR 31. That's this. So that fills this with some sort of byte. If this was 0, it would go 0, 0, 0, 0, 0, 0. If this was 1, it would go 1, 1, 1, 1, 1, 1, 1 all the way. So that's the first part. And then here we do another part where we go into the register and pick the sign extender. So 31, I think to 20. And in here, what we want to do with this, I think this is a syntax error, something like that. We're gonna do that, and that gives us a signed immediate I. We concatenated two things into. That gives us a sign. That gives us a sign that we generated from the first bit. Anyways, once we get to testing this code, we'll see if it works. And I can see a mistake I did somewhere here, something like IR here, I think. And I don't think this needs to be in here. Am I right? And probably there's a sign 31. Yes, wire signed 31. Wire signed 31. What did I just do there? Wire lead red capacity. Yes. Wire. Just give me some sort of definition of a wire, please, so that I can actually see it. Please. Yeah, see here, we make a vectored thing. We make something called vectored. So wire vectored and then a capacity here, and then we gave it a name here. So it's basically signed. Okay, cool. Yeah. Let me see something signed. Let me see something signed. Yeah. Perfect. So this gives us, it's a thing that says whether the thing is a sign or is signed or not. Is it signed or not signed? Perfect. Cool. So that's sort of like int or int 32. Let's do questions and then we keep going. Any questions so far? Any questions? No questions? Cool. Shall we keep going? Shall we keep going? Okay, cool. So that gives us a signed, this gives us a signed immediate I that we can operate on. I just, my code feels wrong somehow. I feel like I'd still need here. Yeah. I wonder if I can get an LSP for Verilog. I probably can. Can someone tell me how to get an LSP for Verilog? And then let's actually make a register, a 4-bit register. I mean a 5-bit register. And then here, this, you see this? Once we start doing this, it's going to completely break this. It's going to completely break this. So by the time we're done with all of these changes, remember, because we're now moving to 32-bit instructions, which we're going to change just now. So let's make a register that has the result that holds the register destination. You see here? Let's make a register that holds the register destination, and we're going to use this register to hold the last computation, and then we'll just put the last computation in the. We'll make it so that we can do a few computations, so that when you're rolling through the instructions, you make the LEDs light. Okay, so we can produce like a 1, a 2, a 3, yeah, a 3, a 4. Like we'll produce some sort of sequence that ends up making the LEDs light. Okay, so let's actually just last. written, last written reg, and then we'll do something like let's just say this. Let's leave a comment here. Hold computation for LED. Okay, cool. So now let's keep going. This remains the same. This remains the same, and then this one now. This is also going to disappear completely. So I'll come back and delete this. Let me first of all do everything, and then do stuff, and then go from there. And then also these instructions are now going to change. Maybe not. Maybe not. I think they are going to change, because we're going to start using the we are going actually run our CPU. Since we were like using a toy, it's almost like a toy, what would we call it? Almost like a toy instruction set. So now we're gonna actually start using the RISC-V one. And I think here the new change that comes in is that now we're actually going to be listening. First of all, this is the first place we're going to use those. Let's just put a comment here and say remove after. It's not like we can't go back to it, because we have all of this on Git, so we can always just change this. So the first thing, now we need to do something that enables us. We need to now start branching on the types. And eventually this will actually keep going until we branch on all the types. Instead of like actual raw opcodes themselves, let's start branching on the type of instruction. So right now let's do let's do R type, and then let's do I type. Because we can sort of do that. We can't sort of like branch on the. We can't sort of branch on this, but I don't want it. Okay, I don't want to, and Okay, anyways, let's pick the program counter right now. So let's do program counter is let's set IR to program counter, and then say ROM, and then PC. And remember, the PC is just the address of the PC is just the address of the instruction that you want to run now. Yeah. Writing large systems is hard because you never remember everything. You can't remember everything. You have to forget, and you have to like narrow yourself down in this little part so that you can change something. Okay, now let's switch on the opcode, and you'll see why we made those things up there. So opcode, doesn't that look a lot more I think an end, or is it a brick or an end case? Case. I just want to see what happens when I have complicated case statements like I saw. So case and case and case and case and. Okay, cool. Yeah, that's what I wanted. And case doesn't have a begin. There's no begin. Okay. So what I'm gonna probably do is do a nested one. Case and case. Yes, like that. there's no begin. And then in here, based on the opcode, I will do I can now handle all the like R types, and then I can handle in here. I can also handle like in here I can handle all the R types. So R type. Sorry guys, I'm sort of designing it. This is the whole point of this, to do what I do at work here. So I'm sort of designing this as I go and kind of like trying to remember stuff that I had studied all night last night. Let me quickly jump onto here and see if there's any questions. No questions so far. Thank you, Thomas, for hanging around. Cool, no questions so far. Okay, let's do this. Let's handle R type. And R type already has a how do I say this? R type already has there's a sequence of bits of, let me see, let me just show you. R type RISCV R type opcode. So you see, these are I's, and these are R's. And if you see here 0110011, this is the same opcode everywhere here. So right now we're starting to use this. Okay, so it's going to be something like 7 bits, 7 binary bits, and then they're going to be 0 0 1 1 0 0 1 1. So 0 1 1 0 0 1 1. Is that really it? Okay, yeah, check. It's 0 1 1 0 0 1 1. And then now we can handle all of these. Okay, and today what we're going to do here is actually handle and immediate or immediate, add immediate or immediate and immediate. And then all of these ones will come the more we start adding. But because some of this need like system and something of the sort to be done. And basically, what we need to do is just handle this. This is exactly what we need to do. We just need to do all of these operations. There you go. RD here. I'm being so insane. So here's a reference. We don't even need to think. All of the code is written down. All we need to do is understand it. Here it is. Here's all the code we need to do. In the changes that we need to make. Boom. It gives us everything. So let's do that. And in here, let's say if it's that, let's do a begin. Okay, isn't it that like that? And then in here we have another case, and then in here we can have an end, and then in here we can do funct3, because later we will have to handle this. Where is it? Later we'll have to handle funct7 to extend the opcode, but right now we won't. So right now let's just do funct3. Yeah, funct3. Okay. And then inside funct3, what we're going to do inside funct3 is let's check 3 B 1 2 3. I think I can even go here, control R, funct3. Yeah, you see it's where is it? Is there some sort of instruction I can see? some sort of place where I can see. Yo, I love this. It's just 5 pages. The whole of the RISC-V instructions. It's just 5 pages. So func3. I want to handle func3 for now. And it's just 3 bits. Yeah, there you go. 3. You see? 3. So, okay, cool. So it's case B000, and then in here let's do another a nested begin. And then in here let's do if something like funct7. Oh. So I won't do anything here. It's just, this is just to put it in so that we can come and handle it later. Because I need to know. 1, 2, 3, 4, 5, 6, 7. Okay, I need to know. And then actually, why not just, because we already have the thing. We already have the thing here. Not, I don't want to do atomic. I want to do RV2E. I don't want the compressed one. I really do not want the compressed one. Let's just do the I one at the top here. RV2E and funct7. Okay. Cool. So here we're gonna take RD. Okay. RRD. Okay, R is the current general purpose register, and then we do a non-blocking. R is RS1. We're already handling it. It's fine. Minus RS2. RS2. See that? And then if we do it like that, and then we say this, and then we can label this sub. Okay? And then we can also go here, and then we can do an else, and then we can do a tab. I'll do RD, RD, and then in here we can do a non-blocking assignment operator, and then in here we can take is it RS1? Is it RS1? And then this is going to be plus RS2. Okay, so this is going to give us a sort of extension into our sort of how do we call it? This is an extension of func3. Okay. Okay. No, this is now. I want this here. Case func3. Did I do everything right? Begin. Where's the end for that one? If else and I hate it when it shocks me like this, because I don't know if actually the thing is my issue or I just want it to be here. I just want to be here. So 3B111, and then in here let's do RD, our destination. And then let's do non-blocking. So this is just putting back the ones that were there before. Okay, so this is I'll put an add over there. So RS1. Okay, and then we can do an AND here. RS2. Yeah, and then we can do that and then that and label this AND. And then in here we can go and do, this is add. Okay, and then the next thing I want to do is 3B, I think this is 110, and then in here we want to do RD, it's always RD, and then we can do a non-blocking assignment operator, and then we can do RS1, and then here we can do an OR, I think. And then when we do here, we can do RS2. Okay. And then that is that. And then we can label that an OR. And then we can do 3 3B, 111, 3B, and I think this will be 100, and then in here will be R, RD, and then non-blocking assignment operator R. This is RS1, and then this is going to be an XOR, and then this is going to be RS2, something like that. XOR. Okay, cool. So that changes that. And then we, as usual with all the cases, we need to put a default. So we can do a default no op, do nothing, and then I think here we can do an end. Well, let's see. Let me see. Yeah, that does an end case for me. This is actually an end, but this needs an end case somewhere in here. End case. And then before we actually do an end case that finishes that, let's do actually after finishing that, let's set last written reg, so that the code in this loop runs sequentially. So do all the operations and then do that is equals that, and then let's put RD in here. Basically, assign it to RD. Because we're still using IR over there, so RD will still work. And then end here works. And then in here, we want to do after that opcode, I want to handle 7 B00100011, and where I'm getting that from is here. Come on, give me my mouse back. Where I'm getting that from is, let's zoom in again, zoom in. Where I'm getting off is there. So we are basically officially getting to handling the things we want to handle this session, which is immediates. If that makes any sense, okay? If that makes any sense, we're handling immediates now, okay? And then begin. And then after begin, I will do some sort of like end case. But this goes in here because this gets its own case in here, which goes something like case, I think, or something like, actually, let's see. I don't want to do that. I want to do something like that. And then in here, we're going to just handle funct3. Funct3. Yeah. Let's see. Let us see. Immediate funct3. Immediate funct3. And then RS is the, yes, RS is a constant. And then we have RD, which is the destination. So do this immediate operation on RS1, and this is the sign. This gives us the sign, this gives us the thing that we want to operate on, and this gives us where we want to put it. And this is the decorator for the operation to be performed. Excuse me. Okay. Cool. So let's try that. So case funct3. Now we need to go and do something like case funct3, and then here we need to end this case, and then here when we do a case funct3, we need to now do something like 3B, and then here they're like B000, it's 000, 111, 110, think something like that. So let's do that. RD is equals to that, and then this is going to be set into, the destination is set into R, RS1, we're taking RS1, and then we're doing some sort of operation straight. We're doing an add I, so it's going to be plus IMM, and then it's plus IMM I, immediate I. And then this gives us an add. This gives us an add I, add immediate. Like you have, this is RS1. This is RS1. So the constant is in the instruction already, and you just want to operate some sort of source with it. So RD. Let's see, and then we'll do this. It will set the RS1. This is the thing that we need to operate on, and then we'll do no, this is not a plus, this is and. So we'll do an and then we'll do an im I, and then this will give us an and I. Cool. And then 3 B, and then 1 1 0, I think I said, and then it's RD. Yes, the destination, and then that is R, and then RS1, and then this will give us an OR. It's an or immediate, isn't it? Or immediate. It's actually not not as or immediate. An or immediate is IM I, and then or I. So this actually, and then I think we need to do a default, as always, default, and then there's that, as always, and then after that we need to do an end case, actually, so that it ends that, and then here we need to do last written reg, and then we need to do an unblocking, and then RD, and then in there we need to do an end now, and then after the end we now can go all the way back to, we can remove all of this. This disappears, and the rest of the code stays the same. That disappears. Actually, after that disappears, this also needs to change. We can't use this anymore because now we're operating on different data. So let's actually change these three as well. And then we'll do questions. It might appear that I'm just using some magic knowledge, but really it's just I read this, and then I read that other this, and then I combine with that. I'm combining three sources, and I'm sort of I spent like 3 hours reading all of these things before, or 2 hours. I would read all of these things before. I would make some notes, and then I would come, and I want to kind of build up I want to build with people so that I can actually find the thing I'm doing. And then this will do this assigns. This is going to be our last written reg. So get the the thing, and then the second one. Remember, last written reg is like the RD. Okay, last written reg, and then this is going to be the one-th, and then here we're gonna get our RD, last written reg, this is also a reg, and then here we're gonna get a 0. Okay, here we're gonna get a 0. So this actually gives us sort of ish working CPU, I think. Here's the problem. Here is our biggest problem right now. We have all of these instructions, but number one, they are 8 bits. They're all 8-bit instructions, and we've moved to a 32-bit instruction register. Wait, first of all, let me pose for questions. Any questions? Any questions by anyone here? Posing. Cool. No questions. That's fine. No questions yet, so let's actually go on to the next part. So now what do we need to do? My mouse died again, and I hate it when my mouse dies. Yeah, I hate it when my mouse dies. So there's this. So now actually let's do something. Let's actually do something that we want to do here. In order for us to test this CPU, this new CPU that we've done, we're going to actually need to kill all of this. This is all garbage. Actually, no, it's not all garbage. We can keep a few of them. We can keep the beginnings, and we can operate on them as let's operate on them as constants. Let's actually just change all of them. Let's change a few of them. So let's make some results that are going to actually give us some sort of instructions. So let's write some binary. So it's 32, and then here instead of let's do H, and then here we can do 0, 0, 5, 5. So that's the immediate and the operation, and then 0, 0, and then we'll do I think 9 and 3, and then this will be add immediate x x1 x0 5. So put in x1 x0 plus 5. Okay, and then let's do the same one here. Not 91. This is 93, I think. And then let's do the same one here. So 32, and then H, and then 0, 0, I think. 3, that is the sign and the constant. And then let's do 0, 0, 1, 1, ray. So this is what? This is going to be add I x1 x2, and then this is going to be 3. So let's actually add some more instructions here before we keep going. So let's do an add, just a normal add, not an immediate add. Add x3, x3, x1, x2. Add it 2. And then after that, let's do an and immediate. We have an add immediate and immediate, and then this one will take x4, and then this will be x3, and then this will be something like 7. So we get 1, 1, 1. Remember, I'm trying to get like the LEDs to light because the LEDs are set on these things. An or immediate. Let's do an or immediate of x5. Yeah, these are just the instructions, and then x3, and then R1. Okay, cool. And then from here on, let's do nops. So here we're gonna do something like 32 H, something like 1, 2, 3, 4, 5, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. 1, 2, 3, 4, 5, 6, 7, 8. Okay, amazing. 1, 2, 3. Yeah, that's why it's shorter here. Cool. That's fine. And then I want to do SV Y, and then SP just for sanity, because okay. And then soon we're going to be able to start using a compiler. The thing I'm trying to push for is to write a CPU that actually works on an existing. I don't want to make a compiler. I really don't want to. I'm very bad at this stuff. So I do not want to make a compiler. What I want to do is just make a CPU that works with existing instructions. So ideally, at some point soon, I'll be able to write RISC-V. I'll just be able to compile some C using the RISC-V compiler, and I should be able to run it on my CPU, which I've built on my FPGA. And this is actually why I'm trying to really follow the RISC-V standard, because I don't want to make something custom that only I use and stuff like that, stuff of the sort. I want to make something that is usable by everyone, or rather, I want to make something that I can use with existing code. Ideally, I can build this CPU to a point where I can just run Zephyr on it. That would be amazing. Let's actually fix this other instructions here. This needs some thinking. 32H, and then in here we want x1, x2, and 2. So is it an immediate? It's not an immediate. So if it's not an immediate, then it's 0, 0, 2, and then it's 0, 8, and then it's 1B3. I think so. And then this actually needs a H. And that fixes it. And then something here, you want to do 32H, and then this is going to be a 007, and then this is going to be a 1F. So these are those the 213. And then in here we want a 32H, 32H. And then this is going to be 001, isn't it? And then it's going to 1E, and then it's going to be 293. Remember, this is just filling. We're filling this. This is what we're filling here. Sorry, where is it? This is what we're filling here. We're just filling this. We're making a 32-bit hex value that fills this information out. You could as well write. You could also write it in binary, but that would be sucky. That would be very sucky. Okay, so this actually changes our whole CPU. I don't think it's gonna build. I'm pretty sure there's a lot of errors somewhere, so I don't think it's gonna build. So let's do an Appio build. I say it explodes. Unexpected token IREG 22. I expected that. I can't mean line 44. Okay. 21J. I see. '96. This doesn't make sense. So it's like last written reg, and then I need to what? And so end case, last written reg, and this I haven't handled this guy here basically. So let's see. What is it? After last written edge, I need to end whatever I was doing. Cool. And then after that, I need to make a default. And then default, and then that. This is to handle all the other. This is to handles all the other operations. And then in here, I want to do an end case. I think that's the one. I think this can be tabbed a little. Yeah, let's see. Yeah, so it goes with the other ones. I still feel like there's an error there. I don't like adding that much code at once. I don't believe it. I don't think it works. I think it barely even works. But you know what we can do? We can actually test it and see. That's the old code. It's gone now. We can do iceprog, build, default, hardware. There. It's funny, I don't know if you've noticed, the builds are starting to take longer. This is insane. I think there's something wrong. I don't think the blue one should be like that. It's quite focused on the blue one. Yeah, and we never get this red one working. So, but you can actually see our instructions running. This is actually insane. So the blue one, the last one is always set, it seems like. This is insane. This is utterly insane. Utterly insane. Git status. This is a big change. Git diff. I, for one, am shocked that actually something is working. I'm insanely shocked, and yeah, I'm gonna stop there today. I'm just so happy. Git commit dash v. Git add main. Git commit dash v. So. Add immediate type handling. This implies a few changes. Move to 32-bit instruction registers. And then after that, what else did we do? Move to 32-bit registers. Add wires to access register instruction register instruction IR subcomponents. And then the next thing we do here, is handle R type and I type in opcodes. Handle I type and R type in opcodes. Amazing. Our CPU works. I'm just so shocked, and I can see something. So it's always green and blue, and that's because all of the instructions that we've given it, this is what they're giving us. I'm insanely shocked that it works, and I'm just gonna stop there. This is so cool. Git status, git push it's not gonna like that. Git push. I should remember how to do this every time I do a set upstream origin PR IM type. Amazing. Let's open a PR and we're done with this today. I'm so shocked that we're gonna end up with a RISC-V CPU. That's insane. We're gonna end up with a RISC-V CPU. We really are. Yeah, it's fine. That's a good message. Create pull request. Yeah. Okay, anyways, it's been an awesome session today. Thank you all for showing up. Thank you for the people who left questions. Remember, in the link of the video, there's a link to the community, our Discord server. Please do join our Discord server and let's hang out and let's suggest to me what I should do next. Okay, and then what I'm gonna do is I'm gonna edit the adding immediate type instructions to our RISC-V CPU. That's really it. That's what we did today. Thank you all so much for showing up. Thank you for hanging out with me. That's been amazing. I'm going to stop this now and we'll see you guys tomorrow, or guys and gals tomorrow. And thank you so much.